To find life beyond Earth, we first ask a simple question. Where can liquid water exist? Liquid water is essential because it is the primary solvent for all known biology. On Earth, water cycles constantly, managing heat and distributing nutrients globally. The Earth's orbit sits perfectly in a region of space called the Habitable Zone. This zone defines the range of distances from a star where water remains a liquid. Too close, and water instantly boils away into the planet's atmosphere as vapor. Too far away, and all the water freezes into hard, solid, unusable ice. The challenge is that this zone is not fixed. It is constantly shifting with the star. Even a slight change in solar radiation can push a planet out of habitability. Imagine a planet slightly closer than Earth, receiving just 3% more light. That tiny increase can trigger a devastating and irreversible greenhouse effect. Therefore, the search for life is actually a precision hunt for the perfect orbital sweet spot. We call this perfect distance the Goldilocks Zone because conditions must be just right. This idea relies on the balance between stellar heat, orbital distance, and planetary geology. A thick atmosphere traps heat, which widens the habitable zone slightly outward. But a strong solar wind can strip away an atmosphere, shrinking the zone inward. Thus, the definition of the habitable zone is dynamic, not a fixed line in the cosmos. Only one place can support life as we know it, the surface of a liquid water world. This blue marble is our baseline, but the cosmos has many stellar possibilities. Next, let us map our solar system's habitable zone to see its actual limits. On the diagram, our Sun sits at the center, radiating energy outward in all directions. The habitable zone forms a thin, donut-shaped band around the entire star. For a star like our Sun, this zone extends roughly from 0.95 to 1.7 astronomical units. The inner edge of the zone is where incoming light heats the surface above the boiling point. At the outer edge, the stellar flux drops too low to keep surface water from freezing. Our planet Earth sits perfectly at 1.0 astronomical units from the Sun. This orbital distance provides the correct temperature for liquid oceans to form. Let us examine the planets near the inner edge of our Sun's habitable zone. The planet Venus is a perfect example of what happens when you cross that inner line. Venus sits at 0.72 astronomical units, receiving too much solar heat. Its water boiled away long ago, leaving a dense, suffocating carbon dioxide atmosphere. This is called the runaway greenhouse effect, transforming a world into a scorching hellscape. Inside the zone is Earth, our single point of comparison for life. Now let us look at the planets beyond the outer edge of our habitable zone. The planet Mars is a case of a potentially habitable world freezing into cold storage. Mars orbits at 1.52 astronomical units right near the outer border. Although it has large underground ice reservoirs, its thin atmosphere cannot keep surface water liquid for long periods. It is currently too cold demonstrating the critical importance of atmospheric pressure and insulation. So, in our solar system, only Earth occupies the true Goldilocks zone for life. But what about other stars? How do their Goldilocks zones compare to our Sun? The mass and luminosity of a star determine the size and distance of its habitable zone. A very hot and massive star, such as a blue O type, shines intensely and lives briefly. Its habitable zone must be located extremely far away to avoid boiling everything off. Such stars also burn out too quickly for complex life to have time to evolve. By contrast, a medium star like our yellow G-type Sun has a moderate and stable zone. G-type stars can burn steadily for 10 billion years, allowing ample time for evolution. The habitable zone is directly proportional to the star's luminosity squared. This means the zone for a very bright star is much wider than for a dim star. Conversely, small, cool, and dim red M-Dwarf stars are the most common in the galaxy. These M-Dwarf stars burn their fuel incredibly slowly and can last for trillions of years. Because they are so dim, their habitable zones are located extremely close to the star. For Proxima Centauri, the nearest star to us, the habitable zone is within Mercury's orbit. A planet in this close orbit may complete a full year in just a few Earth days. This proximity immediately introduces severe complications for any potential life. The stellar type defines the entire orbital geography for life to take hold. Therefore, planet hunters prioritize G and K type stars for their stable Goldilocks zones. On the diagram, observe how star temperature shifts the entire habitable zone outward. An M-Dwarf's tight zone is just a fraction of the size of our Sun's own region. This proximity and stellar variation force astronomers to rethink the definition of habitability. Next, we investigate the specific challenges of M-Dwarf star systems. The main challenge for planets orbiting a cool M-Dwarf is called tidal locking. Because the habitable zone is so close, the star's gravity locks the planet's rotation. This means one side of the planet is in eternal day, and the other side is in eternal night. In this configuration, the day side becomes scorching hot, and the night side becomes frozen solid. This dramatic temperature difference creates catastrophic winds sweeping the planet. If the planet has a thick enough atmosphere, it may redistribute heat to the night side. But tidal locking can also freeze the planet's magnetic dynamo, which is vital for protection. This magnetic field protects the atmosphere from being slowly stripped away by stellar flares. M-Dwarf stars, though dim overall, produce incredibly powerful and frequent flares. These flares can blast a planet with intense ultraviolet radiation and X-rays instantly. Without a protective magnetic field, the atmosphere erodes rapidly from the star's constant assault. This stellar activity reduces the chance of long-term liquid water on the surface. On the diagram, the tightly orbiting planet is constantly bombarded by stellar radiation. The planet's magnetic field must be incredibly strong to withstand this intense pressure. So, while M-Dwarfs offer billions of years of longevity, their flares pose a significant threat. Astronomers are developing new models to account for this tidal locking and flare threat. We are learning that the perfect orbit is only the first criterion for habitability. A planet needs a strong magnetic field and a robust atmosphere to survive these extreme conditions. Next, we will look at two of the most famous M-Dwarf systems, Proxima b and TRAPPIST-1. These close neighbors highlight the complexity of the habitable zone definition. TRAPPIST-1 is a remarkable system with 7 Earth-sized planets orbiting a tiny M-Dwarf star. 3 of these planets, designated E, F, and G, orbit within the star's close habitable zone. All 7 planets are likely tidally locked, facing the challenges we just described. However, their close proximity also creates powerful gravitational interactions between them. The constant tugging creates internal heating inside the planets, similar to Jupiter's moon Io. This geothermal heating could sustain pockets of liquid water beneath an icy crust. These subsurface oceans are protected from stellar flares and surface radiation. This opens the possibility that life may exist not on the surface, but deep inside these worlds. Now we turn our attention to Proxima Centauri b, the closest exoplanet to our Sun. Proxima b orbits a red dwarf star just 4.2 light-years away from us. It is slightly more massive than Earth and sits squarely in its star's habitable zone. But Proxima Centauri is known for its intense and unpredictable stellar flares. The flares from Proxima Centauri could have sterilized the planet's surface completely. These two systems prove that simply being in the Goldilocks Zone is not enough to guarantee life. We need to analyze the atmosphere of these planets to fully understand their potential. Webb Space Telescope now allows us to look for the chemical signatures of life. The light from the M-Dwarf star passes through the planet's atmosphere during a transit. Gases in the atmosphere absorb specific wavelengths, leaving a chemical fingerprint. By measuring these fingerprints, we can search for gases like oxygen, methane, and ozone. The presence of these gases together would be the first true biosignature. Ultimately, a habitable planet needs 3 specific ingredients to sustain surface life. First, it needs a stable star that lives long enough for complex biology to evolve. Second, it must orbit inside the Goldilocks zone to maintain liquid water. Third, it must have a magnetic field and a thick atmosphere for long-term protection. The search has shifted from just finding the right distance to finding the right planet. Astronomers are no longer limited to searching for Earth twins around Sun-like stars. Even tidally locked worlds with subsurface oceans are now considered viable candidates. The James Webb Space Telescope is now pioneering the next phase of this search. Using Webb's data, we can finally begin to exclude the unviable targets. Every new discovery refines our definition of where and how life can take hold. If life exists elsewhere, it must obey the same laws of chemistry and physics we observe. We will find the true signs of life in the unique chemical fingerprint of an alien atmosphere. This chemical analysis must be combined with the physical context of the star system. The habitable zone is complex, but its definition focuses our most powerful instruments. The first detection of an exoplanet biosignature would redefine our place in the universe. A single confirmed signal of biological activity will change human history forever. The perfect orbital distance is just the beginning of this incredible journey. Webb's first confirmed biosignature may be revealed within the next decade. Until then, the search continues across millions of stars and billions of planets. This persistent quest to find liquid water defines our place in the cosmos.